Good morning, everyone. So today I'm going to present our paper, which has a title of Important Guidelines on the Finite Element Modeling of Micropiles. And this work has been done under the supervision of my professor, Dr. Hani El-Naggar at Dalhousie University. So the outlines of the paper or the presentation, I will go through the introduction first, then I will move into the modeling of micropiles in Plaxis. I will talk about effects of the installation process and the increased KS method and the micropile elastic modulus. And finally, I will summarize the conclusions of our study. So talking about micropiles, the micropile is an ordinary pile, but it has a small diameter which is less than 300 millimeters. So in order to gain a good performance when subjected to axial loads or lateral loads, you have to construct the micropile using an advanced technique. The Federal Highway Administration in its manual has classified micropiles into 4 groups: type A, type B, type C, and type D. As you can see here in this figure, type A is the ordinary one. It's like board pile. You will pour the grout under gravity head. However, for type B, type C, and type D, the grout will be injected under a very high pressure that can range in some projects from 0.5 megapascal to 1.5 megapascal. So if you inject the grout under high pressure, this will significantly increase the shaft skin friction, and consequently you will gain a high axial capacity. If you use traditional finite element modeling methods that typically consider and treat piles as board pile or low displacement pile, you will highly underestimate the capacity of the modeled micropile. So in light of these points, the present paper aims to highlight some guidelines that every user of finite element software should consider when modeling pressure grouted micropiles. You have to consider the installation process. In order to see the effects of the installation process, in this figure we plotted the force versus the settlement of the micropile for the field results obtained by Kyung et al. For a type C micropile constructed with a pressure of 1.3 megapascal. And you can see here these are the predicted values obtained from Plaxis in case of neglecting the installation process. So here you can see if you neglect the installation process, there will be a large gap between the measured values and the predicted values using finite element softwares. Keep in mind that the interaction reduction factor, which is used to control the frictional behavior between the grout or the soil, between the soil and the grout, should be in the range of 0.95 to 1 to simulate the very rough surface condition of the micropile. The increased case method, it's one of the methods that have been used a lot in the literature to simulate the effects of the installation process. It doesn't mimic the simulation, it doesn't mimic the installation process itself, but it tries to simulate the effects by increasing the radial stresses around the micropile, and this can be done by using an increased KS value. So in Plaxis, this can be done easily by using an increased value for the initial phase, so the radial stresses around the micropile will be high enough to develop a higher axial capacity for the micropile once installed and loaded. So the challenge here and the problem here is where to apply the increased value of KS. According to a study by Nuaim et al., Nuaim et al. Stated that the zone around the micropile, which is affected by the installation process, only extends to about 5 times the diameter of the micropile. So we can conclude here that you have to apply the increased value of Ks to a specific zone around the micropile, which will have a limited width of 11 times the micropile of diameter of the micropile. However, this will cause a problem in the finite element softwares, because here you have an element which is called A, and a different element outside the zone of interest is called element B. At element A, the radial stress will be 3 times the effective vertical stress, and at element B, the radial stress will be lower. It's 0.5 times the effective vertical stress, because here you have Ks of 3 and here you have Ks of 0.5, which is according maybe to 1 minus sine phi. So here you can't find equilibrium. The stress state is not in equilibrium, and this is a problem in plaxes. In the next phase, the plaxes will redevelop a new stress state after the generation of shear stresses in the soil body, and you will find that the horizontal stresses in this zone has been relieved and has been decreased, and this may prevent the achievement of the desired level of radial stresses around the micropile. To overcome this limitation, some engineers maybe intentionally or unintentionally apply the increased value of Ks to the whole width, but this is wrong, and it will generate an unrealistic stress state around the micropile and may lead to overestimation of the foundation capacity. To see this more and more, and to dive through the effect of where to apply the value of Ks, here in this figure we have two micropiles. For the first micropile, Ks was increased over a limited depth, the depth of the micropile. And for the second case, the increased K value of Ks was increased over the whole depth of the model. So you can see here that if you apply the increased value of Ks in the whole model, whether for the whole depth or the whole width, you can find that this will lead to overestimation of the micropile capacity. So not only do you have to consider using a higher value of Ks, but you have also to apply this increased value to a specific zone around the micropile, not to overestimate the axial capacity. The final thing here is about the micropile elastic modulus. In comparison to conventional reinforced concrete piles, micropiles is considered a composite pile. It has a high percentage of steel reinforcement and some grout around it. So, owing to the high percentage of steel used, you will find that using this equation, which is in the Federal Highway Administration Manual, this average weighted modulus will give you a high elastic modulus for micropiles due to the existence of high reinforcement ratio. In these figures, you can observe that if you model two micropiles, the first micropile with maybe 1% reinforcement ratio, the second micropile with a reinforcement ratio of 15%, which is already stated and reported in the literature, you will find that the load displacement response, whether you are loading the micropile in vertical direction or in lateral direction, the difference, or the micropile with the higher elastic modulus will give you a better capacity and a better performance. So use the right micropile modulus in order to give you the best results in plaxes. So here is as follows. It's necessary to simulate the micropile installation process in finite element modeling, or you will get very wrong predictions. The interface reduction factor around the micropile should be taken in the range from 0.95 to 1. Using an increased value of Ks generally leads to non-realistic stress state around the micropile, and even if you use this value, you shouldn't apply it to the whole depth or the whole width of the numerical model. You should apply it to a specific zone around the micropile, and in comparison to conventional reinforced concrete piles, you must correctly estimate the value of the elastic modulus in order to get the best results of Plaxis and accurate results.